All right, so we march on toward the end of Thomas's Chapter 8 here in Math 222 at SUNY Geneseo. On today's show, improper integrals. Improper integrals come in two forms. We'll go calligraphy pen. They come in two forms. One kind of improper integral is when you have a function like so, and you consider an integral that is unbounded on the one side. An integral whose interval is unbounded on the one side. So if you were to take the integral of f of x dx from a to infinity, we would say that this is an improper integral because one of its limits is infinity. The other kind is the kind where your function has a vertical asymptote of some kind. Oh, let's call this b. This should be a b. Where your function has a vertical asymptote of some sort on its interval. So if we were to do the integral from 0 to b of f of x dx, this would be improper because I don't know what to do with a vertical asymptote. And the reason we don't know what to do with a vertical asymptote is because how did integrals come to be? Well, we made rectangles where we used heights of where the heights of the rectangles were values of the function, and at 0, what do we do with that? So let's handle them one at a time. We define the integral from a to infinity of f of x dx as a limit. So what do? We take the integral from a to some place we know about, and then we let that thing get large. Which really is how you would imagine it going anyway. You would imagine saying, okay, I know what the integral is to here, and then I just keep moving that guy further along until I get basically to infinity. We define the integral from a to infinity as the limit of the integral from a to b of f of x dx as b goes to infinity. If this limit exists, we say that the integral converges. Otherwise, we say it diverges. And one of the easiest examples I can think of is the graph of e to the negative x. What do we mean when we say integral from 0 to infinity of e to the negative x dx? What is this area where the interval is unbounded going out that way? 0, infinity. Well, what we do is we take the integral from 0 to b of e to the negative x dx and take that limit as b goes to infinity. Well, you and I both know how this works. This is one of those you sub in your head moments from 0 to b. So, sub in the b, sub in the 0. Remember, it's subtracting a negative. And what do you got? Well, as b goes to infinity, this gets really small. As b goes to infinity, this is still 1. So I get 1. And that makes you ask, huh? I take this unbounded area, and it's 1. And remember, what that means is that the limit of this integral is 1. And that means that I can make this integral I can make this integral as close to 1 as I like just by taking b further and further out. If we were to, in theory, get to infinity, the integral would be 1. Consider the following. This is 1 over x cubed. What if we're finding the integral from 2 to infinity of 1 over x cubed? Well, that's the limit as b approaches infinity of the integral from 2 to b of x to the negative 3 dx. And we know how to find that. We know that this is x to the negative 2 over negative 2 from, eraser, from 2 to b. That's the limit as b approaches infinity of b to the negative 2 over negative 2, and then sub in 2. I think I got that right. Well, as b gets large, that goes to 0, and that goes to 1/8. Again, we have this area that is unbounded on the right side, and yet the area can be made as close to 1/8 as we like just by taking b further and further out. Which makes us think that all of these will be numbers, and then we get this. This is 1 over x. From 1 on out, the integral from 1 to infinity of 1 over x dx is the limit as b approaches infinity of this thing. Well, I know how to do that. That's natural log x from 1 to b. So you sub in b, sub in 1, and subtract. But we know what happens to this as b gets large. That's unbounded. So wait a second. This area is infinite, but this one is finite, but this one is infinite. Yep, that's how it works. Yep. Couple things to think about for you. I'd like to know what that is, and I'd like to know what that is. The one of them is solved with a technique we've studied in this chapter. The other is solved with a technique you knew coming into Calc 2. But we ought to know how to do this when we gather in our class time. The other kind of integral that pops up, oh, what are we up to, 4 now? The other kind of integral that pops up is this kind, where you have some function and that's okay, but this is not. And so the way we handle that is we go to some number a, we take this area and then push a closer and closer to 0. So this is the limit as a approaches 0 of the integral from a to 9 of 1 over radical x dx. It's as a approaches 0 from the right, incidentally. So what does that mean? It's the limit as a approaches 0 from the right of the antiderivative between a and 9. So how does that work? Well, we sub in the 9, and we sub in the a, and we see what happens as a gets closer and closer to 0 from the right. That's 6. This whole area that is unbounded this way is 6. Can be made as close to 6 as you like just by taking things a little closer. Just by taking things a little bit closer. I'll give you one more shot at it. Let's take a look at the integral from 0 to a half of 1 over x dx. Again, it's a situation where there's a half, and this area is unbounded going this way. So we pick some value a, do an integral from a to a half, and then push a closer to 0, and we see what happens. This is the limit as a approaches 0 from the right of the integral from a to a half of 1 over x dx. And we again know what the deal is with 1 over x. This would be ln of x from a to a half. So you have ln of a half minus ln of a. And as a gets closer and closer to 0 from the right, this gets closer and closer to negative infinity. So number minus negative infinity blows up. And so we say that this integral diverges. So what should you know how to do? You should know how to do the integral from 0 to 1 of 1 over x squared dx. Does that converge to a number, or does that diverge? Okay, so that's what we should know coming in a class on Friday. Looking forward to seeing you there. Until next time, America.